I see it's 10 a.m., so as promised, we'll go ahead and start on time. Being a Toastmaster myself, I always feel it's important to start meetings on time. I imagine hopefully we'll have some more people join us that are maybe just struggling with getting the Zoom software going, if it's their first time using Zoom or what have you. So I'll kind of do kind of a brief introduction about the scientific photonics, and then we'll hopefully use that to kind of buffer a little time for any latecomers, and then we'll go ahead and get right to it, to the LaserSafe PC. So hopefully everybody on their screen can see the scientific photonics page and see this is the landing page, or the home page, that we currently have for scientific photonics. And scientific photonics is a woman-owned small business. It's actually a minority-owned, woman-owned small business. So there are certain tax advantages for some organizations here in the United States for doing business with us. Since we're not CPAs and accountants and tax attorneys, we're not going to go any deeper than that, but they're certainly worth looking into. We currently represent the LSPC software, which Patrick is familiar with, and I see a couple other people joined us. Welcome. We also represent the Noir No IR laser shield, the laser safety glasses and shields. We also represent some other products within the photonics and laser industry, but today we'll be talking about the laser safety software. And so we have this page for our software. And with here, we have one page that we're gathering the laser safety compliance. We're gathering articles and reference links to various articles in OSHA that are basically pointing out that people are getting sued and for not being compliant, for injuring patients or employees, by not being properly safe with their lasers. And these days, with lasers being manufactured all around the world and not so much just in the United States anymore, some areas are using even the old Cdrh standards. Some areas are using the European standards, some are using the American standards, and that's one thing that really makes the LaserSafe PC software so valuable, is because it'll help you, as you'll see in a couple of minutes here, it'll help you check to make sure you're compliant with all the standards that have been used that are out of date, like Cdrh, or which are current. With this also, if for those of you, now we know Patrick is using the software, but we also know that some of you may not be using the software yet. You can download the free demo, and it's about 50 megabytes. You'd go here to the demo, click on that, and that will obviously, you can see it's no cost. There's a short video that I made to kind of quickly show you how to install the software and to open it up and get it going. But it's pretty easy. There's kind of a brief little thing. One thing to note is that it only does 996 nanometer, but basically everything else is the same, with exception to the assistant, which you'll be seeing in today's webinar. The assistant is a very helpful tool. That's also been reduced down, keeping the proprietary stuff, I guess, proprietary, not shared on the demo version. But if you wanted to download the demo version after the webinar, if you haven't already done so, you're welcome to add it to cart. And it doesn't require a credit card. It just requires you to enter in you just proceed to checkout, enter in some information, your name, your company name, your email address, and basically it'll just let you download it. Like I said, I have a short little video there that takes you through the whole process. I don't want to waste too much time. I see we now have quite a few participants coming into the room, so thank you for the participants that are joining us. Now with that, since it looks like we're a couple minutes past 10, oh, incidentally, last one, well, here's where you can buy the software, single seat. We have it on sale right now. If you are looking for, if you have a large facility and you need multiple seats, we have bulk pricing on entire facilities and such. So there's significant savings if you're going to be buying multiple seat. And with laser safety webinar, that's we set that one up just to basically show the schedule of upcoming webinars that we'll be doing. Obviously, this one is listed for today. Based on the popularity and success of today's event, we will decide when to host the next one. Hopefully, there'll be enough demand. I think Jim and I have talked about it several times to do it at least every quarter, but maybe even do it even every month if there's a high enough demand. So please be sure to have your questions ready, because Jim will be able to take you through the software and show you with the questions and everything. Real quickly, over on our Facebook page, if you guys are into Facebook, love it if you go to our page. It's just Facebook.com/scientificphotonics.com, and go ahead and like the page. We could use all the likes we can get. I think we have, I'm not sure how many likes we're currently at, but I know it's several hundred, which is nice. Of course, we're on Twitter, and of course, we have our videos up on YouTube. So with all of that, I will go ahead and turn this over to Jim and let him talk about a little bit of the brief history of LaserSafe PC and GL services. And Jim, why don't you go ahead and introduce yourself and take it away? Jim, I think you're muted. Why don't you unmute yourself?
Yes.
There we go.
Sorry, my apologies. I don't know what happened there. I just keep muting away. But anyway.
Yeah, incidentally, we should point out, when we tested the Zoom software about a week ago, we did have a couple of problems. Jim is in the UK, in London, and we're here in the States. And we know there's several people that are, I guess, one up in Canada at least. And so we know it's all, there may be some delays with the Zoom software, but we're hoping that we won't have too many interruptions. If there is an interruption, we do apologize in advance, but it'll be brief, and then it'll subside. But hopefully we won't have too many, if any, today. Now I'll be quiet.
Shut up, Eric.
Okay.
Anyway, hi. Name's Jim Webb. I'm based in the UK. Been a laser safety officer for quite a few years now, and I've been working with lasers since the late 70s. So I go back a day or two. And one of the things that anybody who's been involved in laser safety will know is that sometimes you've got to make a really, really fast assessment of a situation, especially if you've got about 2 or 3 sites to do in a day. So having with some stuff I was doing quite a long time ago for the BBC, excuse me, they're asking me for some details, and I wrote an embryonic version of this, and it proved to be so useful that I got asked whether I'd like to do a full-blown scientific, which I did, and it's absolutely invaluable to me, because within seconds in some cases, I can assess a situation very, very quickly, and we can say, yeah, we got a go situation, no go. Based on the results, we can make recommendations of what to do, etc. And the software actually went out in 1992. So we've got a 25-year anniversary happening, or is it 35? Anyway, my math's rough. But anyway, that's the general brief overview of LaserSafe PC, how it came. On the screen, you can see, we haven't filled up the whole screen, doesn't matter. When you start up the software, this is the page that you see. And essentially, it gives you a quick idea of what you're looking at, indication of the classifications, etc. It's always useful to read the assistant, just to get an idea of what it's all about. It gives you details about how the calculations are carried out, accuracies, etc., how assistant works, and what the tools at the top mean. The important things to be looking at is where I'm pointing on the mouse. That'll open up the small point source window for intra-beam, for small points. No, there's point source lasers for intra-beam viewing, which translates into English, you get the beam straight in the eye. This is for extended sources, large sources, again intra-beam. This is for fiber optics. Again, specific fiber optics are a specific case. This one's an odd one, because this is to do with LEDs, and LEDs were originally in the EN 60825 European standard in 2001. as LEDs started getting brighter, they felt they ought to include them, but then they realized very quickly that LEDs are not like lasers. So they got dropped in 2007 when the next standard came out. But we've kept them in there more for historical reasons, to be able to get a feel for just how hazardous these things may or may not be. Next part is diffuse reflections, where you have a laser beam falling on a surface, reflecting, and you want to know if there's any potential dangers in that. Next one is scanning systems. Again, you do your calculations for scanning beams intra-beam. Other three sections rather, ALMPE. Those of you, of course, who are familiar with the tables, with the standards, they have tables which give you maximum permissible exposures and accessible exposure limits. And this is a means of accessing these directly instead of having to trawl through the tables, and it does the calculations for you. This one is, well, I'm going to click on this. This for the product classifications. Currently, you can see I'm set to EN 60825, 2014, latest standard. And this is a quick overview of all the standards. Click on that, and there's your overview. And of course, you can see you've got all these are the standards that are defined, or the the classifications which are defined in the standard. You click on each one, and it gives you specifics of what they mean. This one's an odd one, 1C. It's only included in the European standard, not in the ANSI. So if I click on ANSI to select that one, that disappears because it doesn't exist in the ANSI standard, and that tells you the ANSI ones. Okay, and if you want the Cdrh values, there they are. For those who still know and love Cdrh classifications, yes, well, 2A. Anyway, okay, we'll drop this window. The last one here is actually a very quick basic page on hazard overviews, which gives you a help as to how to interpret things, how to achieve safety, etc., what the various values mean. Always worth reading this. Helps. Even today I refer to it, even though I've been on the circuit for years, I still like to remind myself of various things on this. Okay? I'm going to take you through a calculation here just to see how easy it is to work this. Now I'm clicking on this. Come on, baby. There we go. We're up and running. Okay. First thing that you see, the assistant has now changed, and assistant will always track where the window is. Come on. Being in remote control, unfortunately, things don't work as quickly as they would do. This is not representative of how the software would work on your desktop or laptop or whatever.
On my end, it seems to be coming through pretty good. So hopefully it's coming through for everybody else fairly good. It's
being very slow for me, but we assume it's part of the fact that it's on the internet.
Yeah.
Because I'm controlling your screen at present. Anyway, every time you move into another window, assistant will change to help you with what the values are. So we'll enter here. Let's say, for the sake of argument, you're a holographer. You've just gone out and bought yourself a nice 25 milliwatt Heaney from somebody who had a spare one lying around. Heaney being 6. Okay, I'm going to keep talking. If anybody can hear me, I'm going to keep talking. Here we go. I seem to have action on the screen.
Yeah, we can hear you now.
Yeah, the remote control is, we got the values in. Excellent. Okay. 0.25 of a second is a typical exposure time you're going to put in there. And again, notice that the screen has changed. Now, here, this page shows you, or this assistant shows you, how to use the flycons, as I call them. You hover your mouse over this signal here, and of course, you can select repetitively pulsed. There we go. Single pulse, etc. We're going to go back to CW, where we were. You also have the option of being able to choose either top hat or Gaussian. And as we're dealing with a Heaney laser, we're going to go to Gaussian here. There we go. Notice this little bit has changed to reflect that it's a Gaussian beam. If I go back to the flat top, there you go. We'll go back to Gaussian. The calculations change internally because obviously the distribution is gentle, and of course depending on the beam size, different parts of the beam will enter the eye. Okay, we'll leave that one. The other flycon you'll notice here is that one, where you can select your watts, milliwatts, etc. Because I was about to put 25 milliwatts in there, but if I put 25 in there, well, it's watts, which is no good. And it's a bit of a pain putting in 0.025 of a watt. So we go to your, come on, baby. Here we go. Milliwatts, and in they go. I'm going to go back to here again. Notice on the assistant, you've got magnitude definitions. Some people get a bit confused sometimes with magnitudes. There they are. This is all the magnitudes which are scientifically acceptable these days. You click on that. Assistant is actually very helpful. It's a 1.5 millimeter diameter beam. So there we go. Again, as I said, I'm a bit of a lazy person, so I'd put a little nicety in there. If it's a circular beam and I've already put 1.5 millimeters in there, I don't want to do that again. So I hit enter on a blank field and it will repeat the previous value. If there was a different value, obviously at that point you'd put it in there. It's a 1 milliradian beam, and lo and behold, with assistant, with the flycons, you can put in degrees if you wish, which we don't want to in this particular case. Okay. Same again with here. It's a symmetrical beam, so we hit enter again, 1 millimeter, 1 milliradian, and we say 1 meter away. Okay. Hit enter, and kaboom! Instantly a result. Not a big surprise, of course, that we're well above the MPE. This calculation really isn't much of a surprise, but there we go. So great, we know we're above the MPE. That little box there is color coded to give you an immediate indication of where you're at. If it's green, totally safe. Yellow, think about it. Orange is a potential hazard up to about 5 times the MPE, and anything above that, you're in trouble. But we don't want to stop there. We need some detailed information about all this. So we now go to the detailed information window, or the details, and these are the details which come up on the calculation. I'm actually going to maximize the screen here because we're going to need a bit more space shortly. Okay. Now, oh, I'm on Cdrh classification. Okay, usefully enough. Notice that the results are coming out. It gives you a test class of 3B, not a surprise. The power is in milliwatts per square centimeter, which is the American way of doing it. If I wanted the results to be in EN 60825, I'll click this button here, and kapow. The results now change to the European standard. Well, European and world standard, really, but we'll go there. Some of the values change, and notice they've changed to watts per square meter, joules per square meter, which is how the EN 60825 standard works. You're looking at some of the results. What do they mean? Okay, NOHD. You got that? You click on there, and lo and behold, Assistant helps you as to what it is. Spot minor axis. Again, you've got lots of math in there to show you how the whole thing has been derived. And indications of how beam diameter, beam divergence will affect the ultimate size of the spot. Other things, limiting MPE, what they mean. You've got definitions, lots of math in there. Again, how the values are derived. For you math junkies, there it is. It's all black and well, light green and black. There we go. Now, beyond that, we've also got skin exposure, which again, you're not going to worry about that. The value is green. NOHD, we know what that's about. It's dangerous up to about 33.5 meters. The important one for this particular application is what's happening on the left, on the extreme right-hand side, because here we've got optical density for filters, but also we have specifications for laser safety spectacles. The old LB numbers and the new the LB numbers. If I click on that, it tells you what that is about. And it's compliant to the latest EN 207 standard. It's 2017. It came out at the end of March. Interestingly enough, one of the suppliers of laser safety spectacles that Scientific Photonics represents actually used the software to specify their their spectacles. If you want to go deeper in to the calculations, you go to the information page, and this gives you more in-depth results as to elements which are used in the standard. You've got C1 to C7, and of course, if you're familiar with the Z136 standard, we click on that, and you then have the more familiar CA, CB, CZ, K lambda, CP, and CE. All the values change accordingly. Okay, I'll stick to the ANSI standard. Again, if you click on this, all the information is immediately available. And also, if you're interested in how the LB or how the LB numbers are derived, this panel here gives you how all the values are derived, because there's certain correction factors, for example, which are, well, there you go. Again, that's the more nerdy numbers, but they're actually very valuable if you're having to specify something very, very precise and you need to write it all down on a report. I'm going to finish off here with this page here, with this button, which is to do with the classification window, which shows you how the software has arrived at the classification that it arrived at. Because you can't take it for granted that it's just arrived there. You've got all the measurements that you've got there, what readings would be measured by your power meter, whatever distances there are, what accessible emissions there are, etc., and where the classification has failed. The 25 milliwatts is above 3R, therefore you go to 3B. It's above 500 milliwatts, therefore it's class 3B. I'm going to minimize the assistant here, which incidentally you can click on that button and that maximizes assistant, or you can click on this button here just to take it right down to the bottom completely, so you can move all your windows freely without assistant getting in the way. So you can take a screenshot of it and do whatever you wish. Okay. Now, you're thinking, so what can I do with the data? If I go back to here, I've got the option of saving this calculation as, there we go. It's saved in the proprietary LSF file format, which appears on the on your Windows Explorer. If you double click on that, the calculation will automatically open LaserSafe PC and present you that calculation, which is a very quick way of getting into an old calculation. I'm going to call this holographer. Come on. Thank you. There we go. Yeah, good spelling. Save. Done. Okay. Now that's available for future reference. Now, the other thing is when you go to these windows here, these are available to save as text files. Again, I'll go save as. And now you've got the option of saving it as a text file, which contains all the information that shows you there. Or you also have the information of saving it as a CSV file to put into a spreadsheet. A very useful facility, this. And depending on which one of these you click, if you save here, you just save that window. If you save there, you save those these two windows here. And if you save here, then you save absolutely everything. Depends how much detail you want to save. So you've got the option of saving just the details, the detailed information, and the classification information. One of the other features, if you want to cross-check with the standards tables, you got the ALMPE table here. That opens up this little window here. And using this funny little button here, which seems to suggest that you can move from one to another, you can take the results of the last calculation that you carried out and plug it in. Kaboom. 632.8, 0.25 of a meter of a second, and there are all the values: class 1 AELs, the exposures for ocular, skin, MPE, eye collection, aperture, etc., and all the other bits of information that you need to know. All that, everything is completely transparent to you on this software. And if I do this, again, just show you how quickly this whole thing can occur. Kaboom. Everything changes instantly to reflect the standard that you're working on. I'll go back to the ANSI, seeing as we're dealing with the USA. Normally I'd be using, being UK, of course, I'd normally be using EN 60825, but we'll stick to these for the time being. Okay.
Jim, I have a question.
Shoot, yes, please.
You have the exposure to the beam time frame as 0.25 seconds.
Correct.
And over on the right side,
when you carry out calculations, you have different time frames involved. I'll go to this window here, which seems to... can you hear me?
Yes.
Ah, good. Okay. For some reason, my screen is frozen. I can't do that. When you carry out classification...
Try it now, Jim, or try taking back... Yeah, it shows your control.
There we go.
Again.
Excellent. On this classification window here, you've also got the time bases available and the apertures. Now, if I hit on T for time base, you'll see here that there are 3 different time bases available: 0.25, 100 seconds, and 30,000 seconds. It's chosen the longest time scale for this particular calculation. If, for example, this was a 4 milliwatt laser, it would then have selected 0.25 of a second.
Okay, these are default.
These are not defaults. These are the requirements of the standard.
Okay, the standard's default exposure time. If you don't know what the exposure time is,
exactly.
Yeah, okay.
Exactly. You can influence it in certain cases by putting in, if you want to limit to 100 seconds for particular reasons. If you put in 100 seconds, it will default to that time that you put in there. But generally, it will use any one of the 3 time bases: 0.25 second, 100 second, or 30,000. Typically, it will default to 30,000 seconds, particularly in the ultraviolet and the infrared.
Okay, thank you, Jim, for explaining that.
No problems. We do remember that the software has to be compliant to the standards, and therefore we have to adhere to certain things. And therefore, this is why this weirdness appears sometimes. That's why it actually specifies that the computation time base is 30,000 seconds. Okay?
Great.
All your answers are there. 99.5% of the answers are actually within the software. Yes, there are occasions where people ask in-depth questions. There was a time when I was getting a lot of questions for the EN207s. And as a result of that, we recently added the green section in the detailed information, especially with the change of the recent standard 2017 for EN207. Okay?
Okay, so that leads to another question. You have the...
Yeah, fire away.
You have the ANSI standard selected at the top.
Yes.
And you have small source details windows that calls out, I think those are EN207 goggle specs, right?
Correct.
I don't think the ANSI calls out goggle specs as tightly as the EN207. Could you comment on the difference between those?
Sorry, I didn't hear the whole question. I'm sorry, you cut out slightly. Could you repeat the question again?
I believe ANSI just specifies OD. They don't have L numbers in the ANSI.
Correct. This is why you have the optical density up the top there, which is the OD. The L numbers and the DL numbers take into consideration the power density which the blocking material is capable of withstanding. In other words, when you look at the tables for these, they take into consideration the power density available by the beam. So in other words, if you have a material which is capable of either cracking glass or plastic melting, that has to be taken into consideration with the specification. So DLB4 is capable of withstanding the power density generated by the beam, as well as blocking the beam through to a safe level. Is that clear enough? Did you hear all that?
And the details of that is found in the EN207 standard?
That is correct.
Okay, thank you.
No problems at all. As I say, the software has to be completely compliant to all these standards, and therefore certain results do look a bit strange. L numbers were an older version. That was the 1998 EN207, which has now been superseded, but people still use those numbers, so we have to have that in there for historical reasons.
Well, and another good example of that, Jim, if you don't mind me piping in, is, a lot of these labs, they have old laser safety glasses laying around in cabinets or whatever, and somebody grabs the glasses and, inscribed on the lens or on the side, or maybe on the case or a sticker or something, it might have like that old DL3, and that's might be all it says. And you're like, well, I wonder if it's, if it's safe now. And if you pull up these results and you see it listed there, then you would be, okay, I guess it is safe.
To use, yes, there wouldn't be a problem. But the thing about the DLBs is the fact that they're a bit more stringent on the ability of the glasses to be able to withstand the power densities involved. And it becomes more critical when you've got pulsed lasers where you're zapping a piece of plastic or glass at high frequencies, which can sometimes have different physical effects on the material.
Right. I guess the reason I guess I was just pointing out is that you keep the historical stuff in there for people that have the older lasers or older safety equipment that has some of the older specs, and it doesn't have any of the newer information on it. So then you can use the software to basically check to see if it's still usable, or if they need to go to our website and purchase a new pair of glasses or a safety shield.
Or whatever the case is. Okay.
Exactly.
So we've run through this example here. The only other thing I will say is you've got this thing here called spectrum. You'll notice that it's a color approximation of the wavelength that you've typed in there. It's a little nicety we've thrown in. That as you put a different wavelength in there, it will show you if you're in the ultraviolet or infrared. It will tell you what region of ultraviolet you're in, UVA, B or C, and if you're in the infrared, if you're infrared A, B or C. It's a little reminder as to where you're at. You think, oh, hang on, I don't think I've put the right spectrum in there, and it's a useful little cross check. As a little aside, there's also another little useful gizmo here called Color Help, which if I click that one in, I'm just going to bring Assistant up here, because Assistant will actually, come on, there he is. It shows you quickly what these mean. That's the actual color of the approximate color of the wavelength that you've got in there. But also it shows you the luminescent efficiency, photopic and scotopic. So in other words, if I shift this, the color changes to give you an approximate wavelength. But also, if I put 555 in here, it should have gone in there, hasn't gone in, never mind, we still have a little bit of it, yep, we've got a problem there. It took a while. Anyway, 555, photopic is efficiency of 1, photopic is of course daylight adaptation, scotopic is nighttime adaptation, which the daylight peaks at 555, the nighttime peaks at about 507. There we are, 506, 507, close enough, peaking to 1. The interesting thing about this is, of course, you get to the red, and you've got virtually no red sensitivity at all, which is about normal. Everything at night goes a bit blue-green. Anyway, enough of that. I'll just drop this guy down below. Notice it, the Assistant went to the first active screen. The Assistant always follows the screen there. But I'm going to minimize it for the time being. Okay, right. We've run through this calculation, just a little quickie on a CW. I'm going to now open up the floor to anybody who might have a little calculation they might like to try out, just that might be something they're working on.
Well, one thing I'd like to jump in with real quick, Jim, is
Please do.
Saving the searches. So some of these facilities have lots of different lasers, lots of different configurations, lots of different safe rooms or whatever, whether it's a manufacturing facility or a hospital or some other type of lab. And that's one of the great features of your software that I was hoping you might cover right now for them.
Well, I'll just click on this and open this up. This is one I saved before. There we go. Different wavelength. Different situation, and this particular one happens to be a pulse laser. Notice that all the other results became redundant, so we're now just to here. We can now pull up the results for this lot, and I think we're frozen again. Yep, we got the old, here we go. As I say, when it's on your desktop, it does work a lot quicker. It's the fact that we're doing it via the web that things are a bit slower. Notice also that the color codings have all changed because the 3R laser, which comes under the jurisdiction of not it's not a hazard, but it's a potential hazard. Therefore, all the screen here comes out as an orange surround, orange colors, class 3R. Notice also that excuse me, I'm on this window here. Let's go up here and bring up the assistant. Right, we'll click on here, pulse train. These are the various maximum permissible, because when you're dealing with pulse, you've got to do 3 calculations for single pulse, pulse train, or average MPE. And this gives you all the calculations to do with how these things are derived. Pulse train. The most limiting, incidentally, is always comes up on orange. Okay, so internally, a lot of computations are made, and it will present you with the results. Explorer, you don't even have to start up the software. You want to go into a calculation immediately, just double click on the .lsf file and kaboom, you're in. Shall we try a sample calculation?
Jim, you know, I sort of having an example. One of the things I frequently run into is the laser data sheet will have a Gaussian profile called out in terms of either 1 over E or 1 over E squared. How do you make that distinction here? This is a top
right.
hat.
Yeah, that's a bad one. That's always a problem. Okay, what I'm going to do, I'm going to change this to Gaussian. Right. Now, come on, baby. There we go. We'll take this lot away here. My screen is, I don't know how you guys are doing, but my screen is running very slowly at present. I'm going to restart the calculator.
Okay.
Oh, come on. There we go. Calculation. It's running very, very slowly on this. I do apologize. So I'll restart the calculator. Everything's gone there. If you go to beam diameter here, my apologies. Sorry. I've hidden away. There we go. Now, here you will see that you've got, I'm not seeing it on my screen. There we go. Thank you. I appreciate that.
Interesting.
Oh, yes. This is it. This is
the baby. Right?
Yes.
This is a serious tool. So if I can just scroll this window down, I don't know why I wasn't seeing it on my screen. Thank you, Eric. I appreciate this.
Yeah, that's interesting. You couldn't see that hyperlink.
I don't know why I couldn't see it. Anyway, this gives you a very, very clear indication of what you're reading, where you're reading, even the sort of beam profiles you can have. And sometimes if you have things like 1 over E or 1 over E squared or whatever, it gives you your various correction factors for that. So there's your E1 over E squared correction factor, or if you're using FHWM or D95. Okay, does that answer your question on the Gaussian?
Okay, so in our case, we have a 1 millimeter diameter beam.
Okay.
Up on top in your input screen. Is that?
Yeah, currently that's a 1 millimeter, and that would be typically the standard does requires the entry to 1 over E.
Okay, so that's the 1 over E point, and if I have
that's correct.
So if I have 1 over E squared, I would divide by 0.7.
No, you would have to divide by 0.7. In other words, or multiply by square root of 2.
It would be a little bit bigger.
Exactly, it'd be 1.4 millimeters.
Or if I'm starting with a data sheet, it says 1 over E squared, I would multiply by 0.707, and that's the number I would put in.
No, you divide by 707.
Okay, so I'm going to convert the data sheet to 1 over E squared, and I want to input a smaller number to model that, right?
Sorry, my apologies. Yeah, if you got 1 over E squared, whatever it is that you've got, the 1 over E cubed, the D95, is actually used by fiber optic people a lot.
Oh, I see.
So you've actually got 3 or 4 different measurement points. The typical one, which I have on green, and that's accepted both by the ANSI Z136 and the EN 60825, that's the value that you would normally input. So therefore, if you're given a 1 over E squared, it's actually larger than it should be. So you have to multiply by the 0.707.
Thank you for explaining that.
No problems at all. So, do we have somebody who'd like to pose a calculation?
Hi, Jim. It's Ben Thayer here.
Hi.
I was just wondering. Hi, I was wondering if you guys have calculations for lens on lasers. In particular, my application is a 5 kilowatt, 1064 nanometer laser that would go through some focal optics. Do you guys have provision for that?
No, currently we don't. Currently we don't do that. There is, however, we have been asked this question, and we are currently working on a version which will probably come out fairly soon, where we're going to have convergent beams as well as divergent. It's not going to calculate for the lensing because that's an unusual situation. But to date,
well, it's not so much. It's pretty standard, I think, in the industry. So I guess when you guys get to that, that'd be appreciated. I guess we'd have to consider it does converge, but then they would diverge. So
exactly, that's the problem with a convergent beam, and it gets even more complicated because if you've got an astigmatic beam, then you've got 2 focal points as well.
Right.
So yes, we are looking at it seriously, as you can appreciate.
Yes, thank you, Jim. Okay.
No problems. Do you want to run a calculation?
Oh, mine was a lens.
Again, you can select. Oh, come on. Here we go. You can select microns or nanometers on your wavelengths as well, which makes inputting data a lot easier. Anyway, 10.6. Sorry, 1064 nanometers. Yep, time base.
Well, it's infrared, so I think what's the biggest? We use the biggest one, right? Because you can't avoid it.
Okay,
30,000.
30,000 seconds. Okay. There we go. That's a 5 kilowatt. We like this. We like big lasers.
Yeah, this is fun.
Right. Okay. So we now go to the flyout, and it's 5 kilowatts. There we go. I suspect it's a bit bigger than a millimeter.
My beam diameter is 33 millimeters.
33. Right. I'm going to be lazy and just delete that and hit enter. It is circular, isn't it?
I believe so. Yeah. For this.
Yeah. Are we dealing with a Gaussian or a flat top? Is it multi-mode or reasonably clean beam?
It's a clean beam.
Okay. We stick with Gaussian. Beam divergence. Now this is where, this is where we have that focusing problem. Okay. Now, are you looking? The easier way to get around this is what is your beam diameter at the focal point? Are you trying to ascertain the hazard at the focal point, or at some unspecified distance?
We'd be trying to. It's a hazard at some distance, so the NOHD.
What's the focal? What's the focal? Yeah, go on. Sorry.
So beam divergence was about 2 millirads.
2 milliradians.
Yes.
Okay.
I believe that's it.
Okay. What sort of distance?
So is this the hazard distance or the workpiece distance?
Work distance. Or how? What sort of distance would your personnel be at?
Oh, sorry.
What sort of distance would your exposed personnel be at?
Well, for argument's sake, let's say. Yeah, I'm kind of calculating the other way. I'm trying to calculate, I guess, the distance all my personnel would have to be at, as opposed to how.
Well, what's the closest you'd expect your people to be at?
let's say 100 meters.
100 meter, okay, fine. And is this a CW or a pulsed?
CW.
Ah, okay, we're in the wrong region here. So I've got to make an adjustment here, CW. And right, now what's actually transpired is when you change CW, your numbers change slightly because it uses the previous values entered. 1, 2, 3, there we go, 30,000. 5 kilowatts. There we go. Now we're in business. Yes, I think they're going to be in a bit of trouble.
Wow.
Yeah, so typically our application is we embed class 4 lasers into a laser protective housing.
Okay, which is normal.
Right, and then effectively classify them as class 1 laser products.
Mm-hmm. Now, thing is, in this particular case, if it were to escape the housing for any reason, if you look at the details in there, you'll notice that the skin MPE excesses nearly 12 times, which means even that'll do damage to the skin at 100 meters.
Oh yeah, for sure. So typically we again have them in housing, correct precautions and whatnot, but in terms of adding adequate steel underneath, and in our particular application, we don't have it mounted to a robot head. It is fixed mounted.
Okay, that's good.
Shooting down toward the floor, but
that's good, because we have to deal with a lot of industrial situations where you've got robots and things like that, which is one of the reasons why we're actually looking at the focusing element of it. The software can handle these bizarre situations as well. Also, in some cases, some of these beams are scanning and working over the material. And again, you get a situation of either direct exposure to the beam itself or diffuse reflections, depending on how you model it. Sometimes you have to
interrupt. Is there any way the software can tell us the NOHD with all these parameters that I popped in there, instead of me kind of iteratively figuring out what or how far away my personnel have to be?
5.63 kilometers.
Oh, where's that? There.
That's in the details window.
Oh, I see it. Right on. That's perfect. Thank you.
You'll notice it's also extended NOHD, which is for use of optical aids. And there you're even further away at distance, at 40 kilometers. That's a seriously dangerous beast.
Jim, is there something in the standard that says the goggles have to survive 10 seconds?
Yes, there is.
And
the L numbers are specified to 10 seconds. The LB numbers are specified to 5 seconds.
oh, okay. So would there be any reason to put a 5-second or 10-second exposure time in the input?
You put it. It depends on if you're looking. The glasses automatically default to that time period anyway, because the calculations are internally calculated to 5 or 10 seconds, depending on which standard you're using. So the calculations are automatically done for you anyway.
Okay.
You don't have to do that. What you're concerned about is the MPE.
Understand. Okay.
The maximum permissible exposure. So here, you've actually assumed you're going to be exposed to the beam for 30,000 seconds, which is an unreasonably large amount of time. Typically, you'd probably put about 30,000 seconds or 8 hours, whichever comes first. At which point, I think you'd complain very bitterly about it, or you've got to give them about, say, 10 seconds to start feeling a bit warm and get the hell out. Right, let's delete that value there. Right, and put in 10 seconds and see what comes up now. We see now, okay, we're still above 2,000 times the MPE, but at least you're, whoops, what happened there? Oh, okay. We're doing a bit. I'm going to get rid of assistant for the time being. Since assistant sometimes can be a bit of a nuisance, sort of jiggling around all over the place. But the NOHD hasn't changed significantly, even at 10 seconds. When you're at that power and kilowatts, 10 seconds or 1,000 seconds don't make much of a difference. You still get badly hurt.
What happens at 1 meter distance?
Come on.
Uh,
102. You're so large and so. Oh, I see. We got the screen come up again. If your power density is so large, let's say, for example, you've got a beam diameter about at a certain distance, your beam diameter is about 100 or so millimeters. You can be wearing safety goggles there, which is great. Unfortunately, what will happen in that situation is your glasses and your eyes will fall to the ground fully protected, but you'll be missing a head.
yeah, sure. Yeah, thank you.
You'll notice, incidentally, at 1 meter, your MP skin excess is actually 517 times. So you know your hand is going to fry, or your skin, or whatever's coming into contact. And that's there. You can see the beam diameter is 35 millimeters at that distance. So yeah, a pretty nasty looking little beam.
Exposure time for skin. Separate.
There is no such thing as exposure time for the skin. The reason why the 0.25 second is used for the eyes is to do with the blink response. In other words, you've got an incoming beam, there's a certain power. You can shut your eyes and shut yourself down. With skin, the only response that you got is muscular. In other words, you move your hand out of the way quickly. And there hasn't been any research to see how quickly you can do that. Because if you're being exposed to the body, for example, you've got to move your whole body out of the way. If you're exposed to your finger, then you can sort of flick it out of the way. So there are far too many parameters involved in that.
It's a pain reflex kind of thing. Yeah.
In other words, if you put your hand on there in the beam or move your finger through it, you're liable to just watch the end of your finger drop off, which is not an ideal scenario.
Hey, Jim. Sorry, it's Ben Thayer here again. I was wondering if we could easily show the collateral radiation hazards associated with this laser as well. Is that as simple as clicking that button up top?
Right. When you say collateral, I'm not quite sure I understand what you're asking.
So the hazard created from the collateral radiation from, say I'm doing a welding operation, there's that weld arc, right? So
right.
all that kind of diffuse reflection.
Okay, I understand what you're saying. Yes, you can ascertain that by using this this one here. Yep, we're here. Right. Okay. We can run the same calculation here using diffuse reflection. Okay. And
okay, that's great. Thanks. Yep.
Okay. You can see what I've pulled in now. And I can repeat these values here, 1064, 10 seconds, 5 kilowatts. I'm racing through these values. For the sake of argument, the next one, now the disperser, that's how far the object, there we go. I've got the 1 meter in, is the distance from the laser to whatever object you're illuminating. So I'm going to assume a meter here. Beam diameter will be 35 millimeters based on the results there that we're getting earlier. Oh no, 33 millimeters, sorry. Don't need to do that. And enter. And beam divergence 2 milliradians. And let's say you're standing, sake of argument, 1 meter away. Okay? Kaboom. You're right at the edge of being badly burnt. Or in other words, you're within the safety zone, but you're getting a little bit too close for comfort. Okay?
Okay, right on. But there's also an optical hazard associated with that, right? Not just, I guess. This is
the optical hazard that we're looking at right now.
Right. Yeah. Okay.
So in other words, you got the 5 kilowatt beam striking a surface and it's spraying outwards. And remember, you've now got a 1 meter sphere. So your this is the worst case scenario. We're assuming none of the power has been absorbed by the work, and you're reflecting the entire beam around. And you've got a sphere that's a 1 meter radius, and you're dissipating 5 kilowatts within that 1 meter. And that's the potential hazard that you have there.
Okay, thanks, Jim. Yep.
Okay. Does that answer that question?
Yep.
Don't worry about the Gerald.
Any other questions? Anybody else like to fire something in? Because there are hundreds of scenarios that we can deal with here. And the whole reason for the webinar is to actually throw in some of these scenarios to see just how real the situations it can deal with.
Well, we are a couple of minutes past 11 a.m. here in California.
Okay.
So some people probably have to, go, considering we were saying it's going to run roughly.
Okay. Ben, good talking to you. Thanks for coming. Notice you're about to leave.
So yeah, so for those of you who have to jump off, hopefully you can give us some feedback. Also, we will see about maybe doing this. I don't know, Jim. What do you think? Do it again in a month, or should we wait?
We can probably do that in a month. In a month's time, I'm going to be out of the country, but I should be able to, with good internet connection, should be able to do it without too much difficulty.
As far as we're concerned, you're out of the country anyways. For those who joined us,
true. I mean, out of the UK.
Yeah.
Apologies.
He's in the UK, where maybe that's been part of the source of the problems with the internet connection. So hopefully we'll be able to get these resolved either with Zoom, or we will find another provider to help minimize or eliminate these interruptions. Maybe some of you have some suggestions. Be happy to get some emails with some suggestions on that if anybody can help out with that.
Excellent. Okay.
At this point, for anybody that joined us late, again, just wanted to let you know Scientific Photonics is the company that's hosting this, and we are a woman-owned small business. So we do have certain advantages for a lot of these government agencies and large organizations that can benefit from tax credits and other credits by purchasing through a small business owned by a minority woman. So always like to point that out. On the website, if you want to get your own demo software, you can go to the Scientific Photonics and click on the demo software and download certainly a free copy of the demo software. No credit card information required. As a reminder, you're also welcome to purchase the software. Single site license is on sale right now. If you have a large facility, you need multiple licenses. We certainly have great discounted pricing, and we can quote that individually for you. So just please let us know. And then when we pick a date, we will post it here on the Laser Safety webinar. We'll also be putting it into our newsletter, so please take time to sign up for our newsletter. And we appreciate everybody who showed up for the live presentation, and this will also be archived as recording. I may have to go through and clean it up with some of these hiccups in the recording, but we'll do our best. So with that, if there's no more last-minute questions from any of the participants, we will wish you to have an excellent day and an excellent week. And we'll hope to see you soon.
Thank you very much.
Thank you, Patrick.
Thank you very much for attending. Appreciate all the questions and appreciate all the comments helpful, and all the comments are in fact helpful. We've not come across anything that wasn't. Thank you once again.
Thank you for the excellent software. Thank you. Yeah.
No problems. You're welcome. Okay, you take care.
You too. Yeah. Bye-bye.
Bye.
Bye, everybody.